Thank you. Okay. Today's talk, what I'll be trying to touch on, is that this new work we have done on score match conditional exponential families for likelihood-free inference with Lorenzo, who's my PhD student, and it's pretty much his work I'm presenting. So I will go ahead with the talk. First, a brief introduction to likelihood-free inference. You have all been listening a lot about it, so I don't need to talk much. But in brief, when you want to do Bayesian inference, given observed data x0, you want to obtain a posterior distribution of the parameter theta, and given the data. And general Bayes theorem tells me this prior, and then the likelihood divided by the marginal. Now we know in general setup, when we do not know M, we still can do MCMC. We can sample from the posterior, but what happens when we do not know the likelihood, which is the P0 if it is not known? And apparently for the likelihood-free inference setups, that's what is the concern. One example I will illustrate here comes from the meteorology with Lawrence 96. It's one of the simplest model when you're considering a 40 like 40 ODEs coupled with the SDEs, and the stochastic part contains this sort of functions. I will not get into the details, but the problem here, you can see it's a 40-dimensional ODE. So your integration, if you want to compute the likelihood, it becomes that many dimension. And so it's impractical, or you cannot really compute it correctly. So computation of likelihood is impossible. So how do we deal? We have heard a lot of different talks. Now, in this scenario, we know that the likelihood from which you can simulate. So we can simulate data, but we cannot compute P0. So until now, and a lot of new methods we have been hearing, the techniques in likelihood for inference scenarios are twofold. The first one is surrogate likelihood type of works, which you heard in earlier talks, like the Bayesian synthetic likelihood Leah was talking about, and some of my work with Michael, last speaker, who has done the ratio estimation things, where we touch on this sort of things when you try to kind of explicitly approximate the likelihood function and use that in some sort of MCMC, SNC algorithms like pseudo marginal type of work. Other way, of course, is approximate Bayesian computation, which the name gives to this conference too, where we try to build an implicit estimate of the likelihood by using statistics and computing a distance between those summary statistics. Now, our idea here was like, can we build a bridge between these two things? And we will be doing that by using a conditional exponential family, and we are going to do a likelihood approximation. And these likelihood function, what we have, it actually is a non-parametric likelihood function, but it has summary statistics. So we can use the summary statistics in ABC setup. And it also, as because gives an approximate likelihood, we can use it in some sort of an MCMC type of approach. We will see that soon. Now, what is this conditional exponential family, and where do we suddenly come up with? So the exponential family density we are considering, it's a generalization of the standard exponential family, where we have the eta theta is the natural parameters. So you have p many parameters. We are mapping to natural parameters ds many. So this eta is a function. We are considering it to be unknown. And then we have the sufficient statistics f, which from the data space rd to we are mapping to the sufficient statistics space rds. And then we have the base measure hx. And then we, of course, we have a normalization constant. Now, these sort of approaches where you generalize a likelihood in known exponential family by parametrizing the natural parameters of sufficient statistics by non-parametric functional assumptions, it's kind of becoming popular in machine learning literatures, where they call these things as energy models. And I mean, if we go back to our Bayesian non-parametric literatures, we have seen density estimation in this sort of type of functions used. But here we will be looking into, can we take these eta and f or h being neural networks, which is another way of approximating functions, which when the function is not known, and how does it work? Now, bringing these energy-based models and what we know in statistics, we can see that this is an exponential family, and we are parameterizing using that. You can think about if we have the Neyman-Pearson lemma where the functional form gives me some sort of a likelihood function, we can also do some sort of similar things. Anyway, we'll concentrate on this one and see how this one works. And there are a lot of difficulties to deal with. And I should mention that while we did this work, we actually used three branches of work from previous researchers, and two specific branches come from one of the best minds at this moment in Finland, Apo Huvarinen. Basically, this exponential family of this sort of form, he explored quite a bit in recent past, and we will use score matching, which also comes from Apo's work, and we have extended that to suit the purpose. And then finally, and Murray from Edinburgh, whose work on exchange MCMC, we will look onto that too. So so these are some notational clarifications. We will consider two functions here, eta bar and f bar. So we're just like taking the log hx inside so that it's a simple bit. Now, if we have that, then if W and eta W are neural networks with weights denoted jointly by some W, we need to know that. And we generate data theta j for an xj, and then we want to, that comes from this joint distribution, and want to learn W star such that PW star x given theta is as close as possible to P0 x given theta for all x and theta. This is some sort of density estimation setup we traditionally in statistics looked into. Now, the problem is that ZW theta is intractable, so you cannot use MLE, you cannot use minimized Kullback-Leibler divergence, and how to do that. Before getting to that, I should also mention that what about identifiability of W in this scenario, and what is, when you're considering this sort of models, is this ZW theta guaranteed to be finite? So there are not a lot of theoretical work there, but Apo Huvarinen has looked into identifiability of the ZW theta. When can you get back W in some of his recent works? We have looked into that. Those you can, if you want to look into them, you can get into our paper with more details of that. And finiteness is not very well known, but you can see that if we are only interested in a small part of the data space, you can just think about some sort of a truncated likelihood, and you put a different sort of likelihood outside, which makes it then finite in a sense. I'm interested to discuss offline of that. But anyway, let's try to solve when we do not have any idea what is ZW, how do we do a density estimation in this setup? So our solution is score matching for fitting unnormalized models. So we are considering a model sort of PWX, where PW tilde is the unnormalized density divided by the normalizing constant ZW, which is intractable, and we want to fit to the data, a simple problem that we want to solve here. Now, MLE is not doable, and there are a lot of work from Huvarinen, and previous speaker Michael has worked quite a bit on that, and then Hinton's contrastive divergence, Dye's works, and all of these things. But here in this work, we will concentrate on Apo's original work from 2005 of score matching to solve this sort of problem. What does score matching does? So score matching tells you that a divergence called Fisher divergence they define between P0 and PW, where this is the form. You can notice that we are considering the derivative with respect to x of log P0x and log PWX, and we are kind of measuring some sort of a distance between them. And as because we take a derivative with respect to x, that cancels out these ZW, as because it only depends on W. So that was a clever trick. And then these divergences do not depend on ZW. And there are a lot of new divergences presently people proposes, but the basic idea basis on that you take a derivative with respect to x. Now, we can clearly see that if PW is equals to P0, then that would be 0, the divergence. But whatever the converse, there are results in Huvarnin's paper that if it is 0, then you get back that PW would be equals to P0. Now, still notice that in this functional form, we cannot evaluate the divergences because there is P0, and we do not, of course, know P0. If we knew, things would not be needed to do anything. So under some assumptions, I will not go into those. You can look into the further details for Huvarinen paper on our paper, that you actually can write this thing in a functional form like this here. It only involves PWs and everything else are constant. So here, this is the first derivative of PW log PW with respect to x's and square of that, and then the double derivative of log PW with respect to the x's. And this just come from a very simple integration, but very simple but very clever integration by Park's trick. And next thing is that in this work of original work of Huvarinen, all of these things was done assuming x is an RD, so it's both negative and positive. There's some extensions of works by Huvarinen in later papers and by Mathis Dieton from some other papers where they try to consider when x is only positive or only negative. But of course, when we are doing these sort of things for a general statistical problems, then x can be bounded, x can be only negative, only positive. So we defined score matching on a transformed parameter space. It's very similar if you're familiar with the STAN, where we do variable transformation and didn't do Hamiltonian dynamics. It's a similar idea. We transform the variable to RD and then do score matching. And all these theorems for the consistency of this score matching is also can be proven very easily. That's what we have in our paper to show that under some assumptions, this consistency still holds. Now we want to extend it for the conditional densities as because until now it was only for x. Now we also have theta and we are drawing those thetas from the prior. So how do we define the divergence? So we notice that we are considering an expected divergence with respect to theta, which is coming from the prior distribution. And the simple trick is this: we compute for each theta the divergence coming from the score matching and integrate over phi theta. And the functional form would be looking like that. And we can borrow results from Arbel and Greton for that. If these divergence is zero, then we can show the consistency result still holds. And we have shown that it also holds for when you have this transform score matching, these results also holds in our paper. So then we are ready for doing the density estimation with this sort of tools. Some further comments is that DFE is independent, so it doesn't depend on the normalizing constant of the PW. And we can apply the integration by Proud's trick on the integral over x under suitable assumptions. The assumptions at least at the end of the talk, if you're curious, we can get to those assumptions, what we needed to prove these results. Now, after we have simulated data, we've chosen this conditional exponential family, and then we have used the score matching extended to this conditional case, and we use this technique to fit that density, specific sort of density, to our data set. What can we do with this approximate likelihood we got? So we'll notice that this PW is exponential family, approximation to P0, what we get. And exponential family is one of the most general family with sufficient statistics of a given size, which comes from this famous Pitman-Koopman-Darmon theorem. And we use these statistics, which we are learning from this FW in ABC. We can use it in ABC. And we can call it ABC score matched. And this should remind you some of the work Dennis originally done, which brought us the semi-automatic summary statistics learning, and which has been extended later by a lot of other papers like Wigvist and all others, where you feed a neural network rather than a linear regression to learn summary statistics given data parameter pairs. So in a same sort of flavor, you can see the summary statistics we are learning, we can use in the ABC framework. And that's what boils down to this ABCSM. And but when you're doing that, notice that you should discard the HW, the base measure, and FW is unidentifiable up to some scale. And we need to rescale the different components before doing ABC. This will also point to some of the works by Dennis where you do this adaptive distance learning for ABC to the second remark. Now, we also propose another framework to not only the summary statistics, but to directly use these approximate likelihood function. Why we do so is because if we have the summary statistics in ABC, when a new observed data comes, you need to run the full inference and you need to do all the inference schemes and all the simulation from the model again, and it's very expensive. But in the next framework what we are proposing here, it where we do not need to do any further simulations. While we trained the model, when we learned the PW, that's for it we needed those simulations from the model. And we know in all these likelihood for inference schemes, the simulation from the model is the most expensive. So if we have done that previously offline, then whenever new observation come, the inferential stuff becomes very cheap. And this is this idea of this amortization in the likelihood for inference setup, what also brings out the second approach we are proposing here. So, but we noticed that we got an approximate of the PW up to ZW. So we do not know ZW. So how to sample from the corresponding posterior. And in this case, we know that for MCMC, we need the ZW theta. So we are actually in this doubly intractable MCMC scenario. So we noticed there are a lot of works for double intractable MCMC, and we picked up the exchange MCMC from Murray et al. From 2012. So the main idea there is that you're constructing an MCMC chain where at each step you are drawing a proposal of theta star, then you're generating a simulation X dash using the theta star, and then using an acceptance rate in like in Metropolis settings, if you're familiar with, then similar sort of acceptance rate here. There are theoretical guarantees for these. But if I notice carefully here from these last two terms, this z theta dash cancels out. So this computation, if you want to compute this acceptance rate, it will not, we do not need z. So it does not depend on the z. So that solves the problem we were stuck with. And the another problem we notice here when we want to use this that we cannot sample from the PW. So we needed to approximate by running another MCMC chain targeting PW. So in a change, in a sense, we are doing two MCMC chains, one targeting the theta, one inside targeting the distribution of the PW of X. Now, that's our proposed algorithm, and we call it Exchange SM. And there are lots of theoretical guarantees for this algorithm available already in the literature, so you don't need to do anything new. And so now, finally, we have two algorithms. One is this ABCSM, and then using the likelihood function we got from this. And you can see that already bridges the two paradigms of likelihood for inference. One is ABC, one is the surrogate likelihood type of works. And now, how does it work in practice? Does it at all work, or all this? So we did try to do some experimental work, and we'll show more results are available in our paper. But we will compare in the likelihood approximation paradigm with the works by the synthetic likelihood, PMC. We'll do population Monte Carlo using synthetic likelihood. And also we'll do population Monte Carlo with ratio estimation works of Thomas et al. 2020. And in the ABC literature, as I mentioned, Dennis's work comes from the semi-automatic summary statistics learning. Here there are work by Jiang and then later in Wigfist. So it's basically the idea is that you want to learn a map from the data which goes as close as to the posterior mean of the parameter. And basically you do a linear regression, and then this S can be a neural network, which has been extended in the Jiang's work and Wigfist work. If you have a time series model, you use these partially exchangeable networks. If you have a different sort of model, you use a more suitable networks. So we also will be using similar network choices motivated by those previous works in when we are doing this our exponential family stuff. And we will compare our results with also these works of Jiang, found in Prangles and others. There are some details we will use simulated annealing ABC. And our experience, we found that's the most like the fastest, and I mean, anyway, it works well. And then population Monte Carlo for the surrogate setups with 10 iterations and 1,000 posterior samples. And we will notice that for the surrogate methods, we needed to, for every parameter theta, you need to approximate the likelihood. So you need to simulate 100 new data. And we note that for our method, we do not need to simulate any further because it has been done previously. Of course, there is somewhere else to pay for that. I will comment that at the end. We will first look into some exponential family models, as because these are the benchmarks. We're feeding an exponential family. Does it work for this case? Can it learn the natural parameters, sufficient statistics in these setups? And we will use some motivations from Appos and their colleagues' work, where they use this mean correlation coefficient to assess how good is this work. And two types of mean correlation coefficient. One is weak, one is strong. The weak one is like embeddings are recovered up to linear transformations or up to permutation. So these are the two criterions they assess. And on data used to learn the permutation of the linear transformation or on the fresh data. So there we will consider all these four setups, and these values, of course, between 0 and 1, these are correlations. And as large as they are, they're better. And we see that in all of these cases, both for summary statistics and natural parameters with the true ones, we get almost 90.9 correlation in this case. And how do the posterior look? So here are the results. We are using this um, on the top row, we have the true posteriors for the beta, gamma, and Gaussian case. And in the bottom, we have the posteriors for those same cases when we are using this exchange SM algorithm. And we see the posterior is a very good match to the true posterior in all of these cases. And I tell you here, we did not use this true summary statistics through natural parameterization. We learned them using these neural networks. I was surprised that it worked that well. And we also looked into the distribution of Wasserstein distances over, like, let's say 100 data sets. From the true posterior, we know in this case it's true posterior, and then what we learned, how variable are they, and then the RMSE between the true and approximate posterior mean over 100 observation. So should note that when we ran the ratio estimation and synthetic likelihood in these cases, we actually used the true summary statistics for those works. And they are, in a sense, performing here best. Of course, if you have given them the true summary statistics, they should perform best and satisfy everything. Still, when you do ABCFP, ABCSM, and Exchange SM, they're rather close to the true performance here. And they're always better than ABCFP, which actually here ABCFP by we mean we are using neural networks suitable for those setups. And Exchange SM is slightly performing worse, as because ABC is better in a sense, as because we update and we simulate more simulation, so it concentrates on the true parameter value farther or posterior better. Then we so and one crucial point that I would like to point on again, that in as because it is amortized, if you have new observations, so if you have one new observation, 3 observations, 100 observations, for our ABC SM, the cost is basically negligible. For inference, you Exchange SM, it does not need any more model simulation. It's fixed. But when you do ABCSM, it needs more model simulation, so it will be expensive. But all the others is just a lot of more simulations you would be needing. So in that sense, it's very cheap to do. And all these neural network training can be done offline, and you can use as many as samples possible beforehand. And of course, you can go for active learning type of techniques to choose which parameter theta combinations you would be using in these cases. And then we look into some time series models, like the very famous MA case. A lot of people already used before for some of the presentations, and AR scenario. And here we use the partially exchangeable networks, as pointed out in Wickfist's recent works, where they show that that sort of neural networks works very well in this scenario. And then compare with the synthetic likelihood and ratio estimation. And we point that in these cases, we do not know what is optimum summary statistics are. So for those two, we just use the first 2-order autocorrelations. And similarly, we see the approximate posterior, it's slightly bit wider, but they are concentrating on the very close to the true parameter value, and very similar to the true posterior as we see in both the cases. So we get quite good performance. And when we look into the distribution of Wasserstein distance and RMSE for this AR and MA model, we can see the performance of ABCSM is actually the best in all of these cases, and Exchange SM is quite good, and it's very close to the other methodologies which has been proposed, notice that it's virtually, you do not need to do any further model simulations when a new observation comes for that. And the similar point to make that it is very cheap, and it's because it's an amortized version. And finally, we will look into the Lawrence 96 model, which we have explained before, which is a 40-dimensional variable. And we integrate on 120 time steps, which is giving us a 40 cross 120 dimensional data. We construct 23 summary statistics, which we use as X in this case, rather than that huge data set, and uniform priors on all the 4 parameters, and fully connected neural networks is used to learn the parameterize the F and eta. And this is the result we get, and the comparison we are doing in this sense, in this case, with the ABC FP, which is a Farner-Prangles method, but using a neural network, and comparing with the XChange-SM and ABC-SM. And we can see that XChange-SM slightly concentrates better, but the performances wise, they're more or less comparable. I will say not much difference I notice in these cases, except the XChange-SM gives it amortized version, which is very cheap than in future computations or learning posteriors later. So that's our final conclusion from this. And the conclusion is that this is a way to learn a likelihood approximation, which is valid for all X and theta. And what we get out of this thing, 2 things: we can get a summary statistics. We can use that for ABC, and which are performing better than the state-of-the-art ones. And on the other hand, we also get an approximate likelihood function, which can be used in this with the double intractable MCMC algorithms. So you probably can look into further more developed double intractable MCMC algorithms, and we can use that technique there, and which does not need any further model simulation. So it's very cheap to do in that scenario. And what can be the future directions, which Lorenzo will be looking into furthermore, that we can fit these neural networks. We are presently using score matching, and it's rather expensive when you're doing that. We can look into, for high dimensional problems, we can look more for cheaper versions of that, like sliced score matching, or there are other objective functions with like Stein divergences and bigger, I mean, there are a lot of works coming out recently, newer works which are cheaper and works better for high dimensional setups. So we will look into more objective functions. And more generally, we will explore other objectives for normalized models for the LIFA setup. And considering learning approximate posterior directly. So in this case, what we did, we tried to fit this exponential family to the approximate the likelihood function. We can also try to do the same directly, trying to approximate the posterior. The benefit is that you are then using the score matching on the parameter space rather than on the data space, where the data space is fairly large. So when we were in the Lawrence problem, we had to reduce the data space to the summary statistics space to be able to do the score matching. So, but if we do it on the posterior space, then we'll be doing on the parameter space, which is generally small, and we should be able to do the score matching more efficiently. And saying that, I conclude. Thank you for listening.
Thank you very much for a nice talk. So according to the official timetable, we've got time for one quick question, but then we also have time for more questions, which I guess we can throw open to all of the speakers. So does anybody have any questions for Rito?
Sorry. If you had heard something. Yes.
No.
I have a question. In that, you build the FW as the replacement for the summary statistic, but why do you have to keep using it in the ABC step? Why do you have to use the exponential approximation a second time or further in ABC?
So doing it in ABC, we are not using anymore the exponential approximation. We just use the FW as a summary statistics.
I thought you had to use the exchange algorithm because you didn't know the normalizing constant.
Yeah, no, I'm what I tried to say that we are giving two ways of doing inference. One would be when we just do pure ABC using the FW, what we learned. And then the other one would be the full exponential family form with FW and eta. Then we need to do the exchange ABC. So that's what our work brings out two different inferential schemes. One is ABC SM using FW, and exchange SM, which does the exchange stuff with the exponential FW and eta.
Okay, I didn't catch that. Thanks.
Okay, so yeah, do we have any more questions for Rito, or can also ask questions to our other speakers from this session? So one thing I wanted to ask quickly is to Rito is, do you have to specify the number of summary statistics in advance? And if so, how do you recommend doing that?
Yes, so at this moment, we fixed it at the same number as the parameters. And I mean, that is actually a very interesting direction to look into. I mean, in some of the problems, let's say in the weather problem, we done that, but we have seen that in some other problems, we don't report in the paper that like after you learn the neural network, the output, you see that there is a correlation. I mean, you can do some sort of a principal component analysis type of thing that you can see there are like 2 or 3 of their linear combination, the most important. So you may choose that to decide how many summary statistics you will be using. But yeah, that's, I mean, also you can do some sort of a loss-based penalization things, but still it's a thing we are exploring how to do or how to choose both the dimensions in both parameter and summary statistic space.
So I did have another quick question, which is, did you try any example distributions where it doesn't fit into, it's not an exponential family, and the number of sufficient statistics is actually the whole data? So something like the Cauchy distribution. I've just done a quick web search, and apparently negative binomial has this property as well.
So I think AR is one of those setups, I would say. Is it AR? I don't think we can write it as an exponential family, can we?
Oh, I don't know.
Yeah, I think that's what is the case. I mean, yeah, Cauchy would be nice to try. I mean, I think you are going towards these misspecified models in general, right?
Yeah, oh, it's a good point. I suppose, yeah, your auxiliary exponential family model then would be misspecified compared to your true likelihood.
Yeah. Yeah, no, we have not looked into that very carefully, but in that sense, I would like to, I mean, you asked 2 questions. One is this, how do you choose the dimension, number of parameter summary, and the misspecified model. One work by Efron was that any distribution can be chosen to be approximated by an exponential family by an infinite many dimensions. So if I can, if we know, come up with an algorithm to learn the dimension, then it should be also give us a solution to the misspecification problem in that sense, based on Efron's work. Yeah.
Okay, so Umberto Piccini has a question.
Yeah, it's not Umberto, it's his PhD student.
I can take multiple shapes.
Yeah. So I just wanted to ask you, so when you specify a model, which is a member of the exponential family, so say it is a normal model with inverse gamma prior, are you immediately restricted to the sufficient statistics? So since for the normal model, T of x will be x and x squared, if I recall correctly. Mm-hmm. So does that restrict you in the number of sufficient statistics that you can choose, or no? Because if it's a Gaussian model, then it's only x and x squared.
Mhm.
Yeah.
So, yeah, in this case, when we are doing it, so basically you can see there's NW, eta W and FW. So we consider both of them, the dimension of their output is fixed, and we fix that dimension at the number of parameters we are learning. So let's say in your normal application, a problem, you have two parameters, mu and sigma. So then it will be 2. We will assume there are 2 summary statistics, and we would hope those 2 summary statistics will be learning R, X, and X squared. And
yeah.
so in those examples, we showed this gamma, beta, and Gaussian case. So we saw that what we are learning, I mean, we can't exactly show that it is X and X squared, but we show that the correlation coefficient is 0.9. So they're learning those summary statistics.
Yeah, it makes sense that they would need to be kind of close to the sufficient statistics, because yeah, but they will be so the dimension of the sufficient statistics will be 2 in that
case. Yes. Yeah. So that's like related to all of these questions. Like when you're in exponential family, that's what happens. But when you are not, that may not be the case. I mean, if you are on a carved exponential family, how do you deal with those things? So, and when the misspecification comes in, those kind of questions comes in. Yeah.
Thank you, and very nice talk.
Thank you very much.
Okay, so thanks very much, everybody. I guess we could wrap up the official session here, but the call can go on if people want to have more conversation.